is that this describes things in terms of connections in bundles. So it's geometrical again, and that's something I can nice and see. Now, I have to skim through this, although this is the key part of the whole talk. You want to see how to construct an algebra, which this algebra is represented by these geometric quantization procedures. I only want to mention here a difficulty of understanding, which I have not quite seen the way around it. How do you talk about local things in the algebra? It's a problem because, you see, if you've got functions, it's fine enough. You can say, okay, as long as they converge in the region, that's fine. But the problem here is, you see, you might think, well, e to the z is a nice function, and you have no problem with it, but what e to the d by dz isn't such a nice function. Sorry, I can't see how many minutes that was. Never mind. It's anyway, the point is 5. Thank you. The point is that what am I talking about? Yes, it's hard to know what you mean by local, because e to the d by dz moves you out of the set you're starting with. I won't stress that, because that's just a difficulty which I never quite see how to deal with. How do you construct these algebras? Well, I'll have to skim through this rather. Here's the 2 form that you have, which is this thing capital sigma, and that's the symplectic 2 form which you're talking about. And this is naturally defined for any curved space. So if I now think of the space n, it's well defined for curved space-time. It's just the space of light rays, and then a space of light rays with the p scaling, that's the momentum scaling, and now with the circle bundle over it as well. So I have that irrespective of, let's say it's globally hyperbolic space-time, and I don't have to care about twistor theory. I can start doing that. Okay, so that's the idea. But now the point is that locally, I try and bring in the twistors. And now that you can always do this, there's a lot of freedom in doing it, but I don't care about the freedom. The point is, can you do it? And you can do it locally just in an arbitrary way. So you can extend as though there was a little twistor space locally. And the question is, how do you globalize that? Okay, let me continue. This is just the geometric quantize again. And let me say explicitly how you do it. What you do, for some reason it's a 2-stage thing, I can't quite get straight. What you do is okay, you've got your 2 form, which is this sigma at the top, and you want to construct the connection on the bundle, which is this operator, that's the line underneath it here. And how do you do that? Well, you want to find out what the p's and the r's or whatever they are, the p's and the, what's the other letter? Q, p and q. And so you need your p's and q's. And the way you do it is to say, okay, you take your form, which is a symplectic form, which is the sigma, and you write that, you split your scalar product, which is w dot z, into e plus f. And there are lots of ways of doing that. And if you do it as naught plus that, or that plus naught, those two give you the representation of these operators on holomorphic functions of z, and the other one gives you holomorphic functions of w. But you can split these things in all sorts of other ways, which gives you a representation of holomorphic functions in other ways. So you can represent this algebra in lots of different ways. You want the freedom of doing it in different ways so that you can use that freedom to give an abstraction to doing it globally, which is the sort of thing you want. That's where the curvature comes in. I'm afraid I have to race through this. Now, how do you do that here? Well, let me just see, what am I doing here? Yes. Okay. Now, suppose I'm piecing together these algebras. Now, that's the idea. I'm trying to piece your whole thing together out of patches. And I've got 2 patches. One patch has your z's and w's. The other one has curly z's and curly w's. Now, you want to preserve all this structure. Basically, you want to preserve the symplectic form. And then you also want to preserve homogeneity. But the symplectic form is the thing you want to preserve. And what you do here is to take a generating function g. That's the way you do it. You have a generating function. You take half the variable from one side, half from the other side, and you go ahead, and it all works beautifully. That's fine. Now, you see, it does seem to give you, I didn't want to do this part quite right. It does seem to give you a manifold. It doesn't give you the Einstein equations or anything. It gives you what's curious is that to describe a curved manifold, you actually need to look at these non-commutative algebras. So I was saying at the beginning that somehow twistor theory is all muddled about when you're doing quantum mechanics and when you're not. You see, in order to get a curved space-time, you need to introduce these non-commutative variables. It's not quantum mechanics. It's still classical mechanics, but you're using ideas from quantum mechanics. So I'm just emphasizing that somehow boundary between classical and quantum is all messed up and fuzzed up, which is nice in a way. Okay, now this is somehow you can describe the points by looking at four-dimensional self-conjugate completely commuting algebras. I won't go into that, but you can get the points back out of your algebra. Okay, it doesn't give you the Einstein equations. How do you get the Einstein equations? Well, you bring in this form, and you need both parts, as I said, all that stuff, or it doesn't work. I struggled over it for a long time. The zero time, is it? Well, I'll just finish quickly saying what I'm trying to say. This is this, you want to preserve both forms at once. And how on earth do you preserve two different forms with one generating function? Well, I woke up one morning and think there must be a way of doing it, and then I realized that you have a completely crazy combination of coordinates. You don't take half from one, half from the other, a complete mixture of coordinates, and you do that, and then you see that it preserves one for, if it has a certain symmetry, which is swapping these ones with these ones and reversing those ones, very easy to arrange the symmetry, that then the form preserves, this generating function preserves both forms at once, so that it does give you the preservation of both forms. And is that the end? Not quite. This is, well, it is the end more or less. I just want to say that what this gives you, what it seems to give you, is a general prescription for the general Einstein lambda vacuums. Now, when I say a general prescription, you can't write it down as ds squared equals something or other, because you've got to go through all this rigmarole that you can produce with the generating functions gamma of this form with the symmetries, which I hope I've written down correctly just underneath it. When you impose those symmetries, this gamma will preserve both forms at once. And then you can construct your points. Well, that's where the difficulty comes. You have your algebra, and in this algebra, you look for those subalgebras, which are four-dimensional, completely commuting, and self-conjugate. Yes, there was a gift from God, I should mention here, was that this thing was to preserve both forms. But you see, what you couldn't do with the original way is to say what you mean in a Lorentzian space. You've got to impose the hermeticity, that W bar is equal to Z. How do you preserve the hermeticity? I have no idea in the way I did it before. But here you can do it immediately, because you look at these things and you see that it's already, the hermeticity is already within one generating function. So you can explicitly represent that too. So you can make it be a Lorentzian space, and it preserves both forms, and therefore the points are these completely commuting self-conjugate four-dimensional subalgebras. And my roommate, Keith Hannibus, I asked him, in Minkowski space, does this work? And he came up with a nice proof. Yes, it does. It gives you the right answer. And it seems to me unlikely that it's the wrong answer when you curve the space, because you get these algebras. The point is that, do they define the points? Well, it's unlikely that in general you get more all at once. The last comment I wanted to make is, okay, this isn't quite the whole story, because I've treated these two forms differently. One of them is to give you a connection in a non-commuting algebra. The other, I haven't done anything with it. Now, does that give you a theory of quantum gravity? So that is really the idea. Maybe it does, because you have now a commutation rule between this is the other form now, the theta form. When you try to quantize that, do a Dirac quantization on that, you have non-commutation rules, which I've written down at the bottom. Now, does that give you anything like a quantum gravity theory, where you have these non-commuting variables where not just the Z's and W's have a commutation rule, but the Z's and Z's and the W's and W's have a commutation rule? And that would be fascinating to look at. Does this give you something like a quantum gravity theory or not? It would be very intriguing to see. Thank you very much.
Questions or comments? Carlo.
The last point, I got lost in, why does the preservation take
Sorry, can you repeat that?
I lost the last point. Why does the preservation of theta give the Einstein equation? I lost that point.
Yes, because I didn't explain it. Yes, you see, you've got these two forms, and the Dirac quantization of the sigma form gives you the commutation rules between the z's and the w's. But the z's commute with themselves. Now, if you do the Dirac quantization procedure, that is to say, you look at the Poisson brackets that symplectic form gives you, that's the dual of it, and then that gives you commutators by direct quantization, and then that's the expression I've got written down at the bottom here. That comes from the Dirac quantization of the Poisson brackets that are the dual of the symplectic form theta, which I wrote down. So this is the place where, if it is giving you quantum gravity, you see, before this, it was quantum ideas, but it was purely classical general relativity. That's the idea. Whereas if you're trying to extend to a quantum thing, you have to do the commutation rule on the theta, not just the sigma.
So what we're saying is that there are no further equations.
I'm sorry?
There are no other equations.
No other equations.
That's the point, somehow.
Yes.
Okay.
That's right. No, these are the equations. Well, I mean, there are no matter fields in this. See, if you want to bring in matter fields, you'd have to put several twistors, I suppose. I had a quick slide earlier on showing you how you might expect to put massive fields in here. But this is all vacuum. Yeah.
If I can make a comment. In Minkowski spacetime, coordinates play a little different role than on general curve spacetime. So they know about metric tensor. They are actually built from the notion of distance. So if we consider generic coordinates in curved manifold, then they don't encode dynamical fields. So if they were supposed not to commute, then they should use metric in their definition. So they should be somehow adapted to given metric tensor.
To the metric. When you say the metric, I should have explained that point a bit better too.
I guess you in your case metric is some secondary.
No, yeah, but you see this again. I didn't stress that point, but it's a good point. You give me the chance to stress it. You see, in twistor theory, it was already a bit surprising with the old nonlinear graviton construction, none of this palatial stuff. In the old construction, if you wanted to introduce a metric, not just the conformal structure, what you do is basically put the infinity twistor in, because that gives you the infinity twistor is what gives you the metric and not the conformal structure. But it also gives you the Einstein equations. See, when you preserve it with the patching together the two pieces of twistor space, you automatically get the Einstein equations even with the metric. So they come together. And that's what happens here as well, which is quite curious. The metric comes in with this form theta. That's the first time you have a metric, you have a distance notion. And at the same time, you get the Einstein vacuum equations. But it's not as though you have two separate stages. You might say, okay, I think that's your question. You want to put the metric in. The way you put the metric in is with the infinity twistor. That's always been the way you did it in twistor theory. That gives you the scale. Here you put the metric in, it gives you the lambda as well. So it's not Minkowski space, it's de Sitter space, if you like. And the metric comes in with the introduction of the theta form. But then the quantization procedure, or if you like, it gives you this thing here, and well, even before you do that, you get the Einstein equations. The Einstein equations come along with the metric, which is sort of curious, but that's what happens with twistor theory.
It's fantastic.
Yeah.
Thank you. If there are no more questions or comments, let us thank again.